Hi students, we're going to talk about rational functions today and how to sketch them. So let's go ahead and start our notes. So our goal is just that we can sketch a rational function. That's going to involve several key features that we'll need to find. So definition here of what is a rational function. It's a function h of x where we have a polynomial function divided by another polynomial function. Okay, so rational, we have ratio, that's your fraction part of this, and we have a polynomial divided by a polynomial. Okay, so I'd like you to take a look at these and try to identify which are rational and which are not, and why. And just a reminder here at the bottom is that a polynomial function is a function such as quadratic, cubic, quartic, so on, but it involves only non-negative integer powers of x. Okay, so that's key. Go ahead, pause, and let's see which ones you get. Okay, so I'm going to go ahead and circle which ones are the polynomial functions. Please notice some of these are trying to trick you just a little pinch. It's okay to have a fraction. We just can't have a fractional exponent. So let's look at the troublemakers, the things that are not going to allow us to call this a polynomial function. We have here a fractional exponent. Okay, we can't have that. We can have it, we just won't be able to call it a polynomial function. We have x as an exponent, so we won't be able to call that a polynomial function. Over here, this is actually x to the 1/2 power. So we know that that's, again, it's a fractional exponent. And then here we have a negative exponent. Oops, actually, this bottom one is okay because that's just 1/9 to the 6th. That's just a number, that's all right. But the -2 in the exponent is actually the issue. Okay, so one of the key features we want to go ahead and take a look at is our asymptotes. And we've talked about this quite a bit, so none of this should be too shocking. In this case, it looks like we have a vertical asymptote here and a horizontal asymptote here. Same with this one. Here's where we have a horizontal, and in this case, we actually have two vertical asymptotes. You're going to see this, where we see some branches and things happening here. And then for this next one, this is what we call a slant or oblique asymptote. We're not going to have to really worry about this too much in this unit, but just to know that that is an asymptote that you might see at some point. Vertical asymptote, we want to look at, let me write this a different way. We want the zeros of the denominator. So anytime I'm dividing by 0, right, when you think about it. And then horizontal asymptotes we're going to look at in more depth. And again, slant, just to know that they're there, but it's not something we're going to focus on too much. Okay, so horizontal asymptotes affect the end behavior. So notice, so let's say this is our horizontal asymptote. This, the end behavior as x goes to infinity, is getting very close, infinitely close to, in this case, the x-axis. And same thing if we look at the end behavior right here, as we have x values getting closer and closer to negative infinity. But here's the spoiler alert, your graph may cross the horizontal asymptote. Okay, it's really only going to determine and affect that end behavior. So notice we have this graph cutting right through it, which may seem a little upsetting because we're always, when we first learn about asymptotes, is you never ever touch them. But again, this is going to be affecting that end behavior. Okay, So horizontal asymptote. So we're going to take a look at this, and here is our abstract kind of definition, and we'll get into some concrete examples. So as your inputs get closer to positive or negative infinity, so again, we're thinking end behavior, f of x approaches some number L. Okay, L is any real number. Then it said that the graph of f has a horizontal asymptote at this line, y equals L. So we can write this, the limit as x approaches infinity for the function f of x is L. And the limit, again, that same function f of x, as x this time approaches negative infinity, is also L. And so that means that we have a horizontal asymptote, y equals L. Okay, now again, very abstract. We'll do some concrete examples to go ahead and hammer this down. All right, so example of finding a horizontal asymptote. Now, what we want to think about is if we're plugging in humongous numbers, really big positive, really big the other way too, negative, right? If we're going to positive or negative infinity, we want to know what's going to happen to this function, okay? What's the output going to get close to? So we can say the limit as x approaches positive or negative infinity for this function, and in this case, we're looking at 3x cubed plus 2x plus 1,000 over 7x to the fourth plus 4x minus 1. Now, I want you to think about this. If I plug something huge in for all these x's, what's going to be the bigger part, the numerator or the denominator? I see the denominator has x to the fourth. So let's say I plugged in 1,000. We'd have 3 times 1,000 cubed on top plus 2 times 1,000 plus 1 more 1,000. In the bottom, we'd have 7 times 1,000 to the fourth. That's going to be significantly bigger, even though we have all this little stuff here. So we want to kind of think logically, what does it look like? Now, we're going to use a method here where we find out what we can multiply by a fancy 1, okay? So we're going to multiply by a 1, but I'm going to show you the one I want you to multiply by. We're going to take the highest exponent, in this case it's that fourth power, and what we're going to do is we're going to multiply 1 over x to the fourth divided by 1 over x to the fourth. Now remember, this is really just multiplying by 1, so it's completely legal, and then I want you to distribute it in. Now, some things are going to start happening here. So let's take a look. We're going to have, we're looking at the limit, what's happening here with that limit. And when I distribute this, I'm going to get 3 over x plus 2 over x cubed, because of course we're canceling where we can, plus, and this is just going to be 1,000 over x to the fourth. That's the numerator now. The denominator, when I multiply it to 7 times x to the fourth, the x to the fourths cancel, so I'm just left with a 7 here. Plus, we're going to be able to cancel an x here. We'll have 4 over x cubed, and then minus 1 over x to the fourth. Now, like, why the heck are we doing this? Hopefully I'll be able to show you why we're doing this. So we're going to plug in really big numbers, okay, something huge, and we want to see what does it approach. So let's take a look here. So if we have 3 over a very large number, 3 over something really big, like say 3 divided by 10,000, do that on your calculator, or 3 divided by negative 10,000. What is that approaching? It's getting very close to 0. So a positive or negative of a very large number. Well, what that means is when I get to really close to positive or negative infinity, this little fraction is approaching 0. It's almost insignificant. Now let's think about the next fraction, 2 over a positive or negative of a large number cubed. 2 divided by something really big times itself 3 times is either a positive or negative spec. It's getting closer and closer to 0. Okay, next one, same thing. 1,000 divided by something really big to the 4th is going to be close to 0. Now, in the denominator, hopefully we can see the same type of thing is happening here if I plug in something huge for x. So we're left with 0 divided by 7, which of course is 0. So this is how we find that horizontal asymptote. It's y equals 0. So for the end behavior, because remember, the horizontal asymptote affects the end behavior, we can say the limit as x approaches positive or negative infinity of this function f of x is 0. Okay, now you will need to prove this. So again, process is important. You need to show me that you understand why the horizontal asymptote is what it is. And I'm going to do another one here so that you can have that practice. Okay, so same thing, same type of process. We're going to find that horizontal asymptote. So we're going to again talk about the limit as x approaches positive or negative infinity, and the function is 6x squared. Obviously, pause me if you want to try this on your own. Okay. So, can you think about what is the highest exponent and what does that mean we're going to multiply by? Remember, it's got to be a fancy 1. It's going to be 1 over something divided by 1 over that same thing. The squared is the biggest. So, x squared. Okay. So from here, again, this is when you distribute, and then of course things are going to start canceling out, which is what we want to see. So we have, go purple here, the limit as x approaches positive or negative infinity. Let's see what happens here. We get, it's just going to be a 6 plus 21 over x to the first minus 7 over x squared over 3, because the x squareds cancel, plus 11 over x minus 3 over x squared. Now remember what happens when I plug in something huge into the denominator. 21 divided by something huge. What would that be approaching? It would be approaching 0, as would this and this and this. So what am I left with? 6 plus 0 minus 0, right? Doesn't matter. 3 plus 0 minus 0, same thing. And so we get 2. So the horizontal asymptote is y equals 2. And our end behavior as the limit of f of x, as x approaches positive or negative infinity is 2. Now again, if you're looking at this, you could quickly type this into Desmos to get a look at the graph. And we're just interested right now in that horizontal asymptote. But you could do a sanity check and look at that. Okay, the next thing we're going to do is we're going to look at page 26. We're just going to do one of these problems together. And we'll obviously do more practice. There's more problems on there for you to try. So the first thing we're going to do is we are going to factor if possible. So this factors into x minus 6 times x plus 2 over x minus 6 times x minus 1. Okay, now we can see there's a common factor that they both share. And so we're allowed to cancel it because, remember, it's connected with multiplication. So we're allowed to go ahead and cancel that out. So this equals now just x plus 2 over x minus 1. Now we need to start finding all these key features in order to graph. So the first thing I'm going to ask you is discontinuities. So vertical asymptotes or removable. So when you cancel a factor with a variable here, x minus 6 over x minus 6, we are removing, so we removed x minus 6. So we have a removable discontinuity at x equals 6. Now we actually want to know where to plot that open circle. So I'm going to go ahead and find out where that hole or that open circle would be. So I would say, okay, 6 plus 2 over 6 minus 1, we would get 8/5. So there is going to be a hole or an open circle, okay, an open point at 6, 8/5. Okay, now where for the vertical asymptotes, where in the denominator do we have an issue? Is there a value we're not allowed to use? And of course, if we substitute 1 in for x, we are going to have a problem because we're going to be dividing by 0. So we know that x cannot equal 1, or the denominator will equal 0. We can't divide by 0. So we have a vertical asymptote, x equals 1. Okay, horizontal asymptotes and end behavior. So again, we're going to take this after we cancel, we'll take this cleaned up version here. And we want to go ahead and try to figure out what the horizontal asymptote and end behavior would be. So this is where we're thinking about limits. So the limit as x approaches plus or minus infinity of, this is called f of x, but now we actually have what f of x is, so I'll get rid of that. Okay, so let's think about what do we want to multiply by. The highest exponent is the first, so we'll say 1 over x divided by 1 over x. Remember, that's just multiplying by a fancy 1. And so we are going to get 1 plus 2 over x divided by 1 minus 1 over x. When I plug in something close to infinity or negative infinity, these become 0. And so this is just 1 over 1, which is 1. So now we can say, okay, the horizontal asymptote is y equals 1. And for the end behavior, the limit as x approaches plus or minus infinity of this function is 1. Okay. Little more that we have to get on here. We have to look for x and y intercepts and then do some sign analysis, and then we can finally graph. Okay, so to get the x-intercept, we are going to substitute y equals 0. So we're going to write 0 equals x plus 2 over x minus 1. We want to solve for x, so I want to go ahead and multiply by x minus 1 on both sides. This just stays 0 over here on the left equals x plus 2, so x equals a negative 2. So the x-intercept is negative 2, 0. The y-intercept, so for this one, we're going to substitute x equals 0. So we would get for this one, we'd say, okay, f of 0, I'm plugging in 0 for x, is going to be, in this case, we're going to go ahead and plug it in to, hold on one second here, negative 2, yeah. You really can do either the original or the canceled one. I'm just going to plug it into the original one. 0 minus 12, and then 0 squared minus 7 times 0 plus 6. And so we would get negative 12 over 6, which is negative 2. So 0, negative 2 is the y-intercept. Okay, sign analysis. I know you're like, oh my goodness, there's so many steps. And there really are quite a few steps, but you're going to just take it bit by bit. Okay, so don't get too crazy, just bit by bit. We want to put the zeros up at the top here. So we know we have an x-intercept at negative 2. We also know for this one, let's see, what's our other issue for this? The vertical asymptote, that's the other issue. So these are the two that are going to be here. And then remember, we go from negative infinity to -2, -2 to 1, and 1 to infinity. What are the factors we're dealing with? Well, after we already canceled, we just have the x plus 2 and the x minus 1. So this is actually pretty nice because we only have these two to deal with. Okay, so if I plug in, let's say -3, I would get a negative. I could plug in 0, I get a positive. Plug in 2, positive. Plug in -3, I get a negative. Here, let's see, a 0, I'd get a negative still, and then here a positive. So now this is going to be the sine of f of x. So multiplying or dividing, you're going to have the same sign analysis. So this is positive, negative, and positive. Okay, so those are your intervals. Now let's go ahead and start plotting the things that we know. So we already know that we have a vertical asymptote at x equals 1. Okay. And sometimes when I do this, I'll just graph it as I go, as I collect information, but either way is fine. Okay, and then y equals 1 was a horizontal. We had, let's see here, we had a y-intercept at 0, -2, and an x-intercept at -2, 0. And the more of these you do, you're going to notice, okay, this is going to be like a branch that's hugging that horizontal asymptote. Then remember we had that hole. So the hole is at, let's see, 6, 1 3/5. So let's see, 6, 1 3/5, something like this. Make sure that you leave that open. You can always plot more points. Technically, I should have another point on the second branch. I'm going to do that real quick here. So let's say we have x is 2, and we go ahead and substitute that in. We'd have 2 plus 2 is 4 over 1. We'd have 2, 4. Okay, so let's see, 2, 1, 2, 3. So right about here, and then I would keep going up. Okay, and that's your graph. So of course they're going to get a little messier. You need to be patient and take your time with your work. So don't rush it. Just find one little piece at a time. Make sure you have your notes handy. You always get to use those. So write things in the margin, write your questions down, and we're just going to keep on practicing. And remember, you always have Desmos as a sanity check. So you can take a look and make sure that the work you've done is verified with that graph.